This meeting is being recorded.
Good day, everyone. Today we are presenting our project on emergency hair fry optimization. Let me first introduce our team members here. Let's start with our first member, Nurul Akila Idris, our second member, Zulhaimi bin Daud, and myself, Chitra Janjeevi. So moving to the project again, in time of crisis, it can be a disaster, it can be a pandemic, logistic becomes a race against the time. Delivering essential supplies quickly and efficiently becoming a critical to maintain the continuity or saving life and sometimes even to supporting recovery. In this situation, we often face a tough reality where cargo planes have restriction on the weight limits and only a subset of the most important items can be shipped. This makes emergency logistics a little classic optimization problem and a highly relevant one. So in this study, we apply a 0-1 knapsack problem to simulate this challenge. Our goal is to determine which item should be loaded to maximize total value without exceeding the aircraft weight limit. Local search helps decision maker find near optimal solution fast by exploring better alternative near and initial solutions. So for that, we are using a local search algorithm implementing using a Excel VBA. Moving to our next slide, we are going to discuss on emergency logistic overview. So in the emergency logistic overview, logistic is not just about moving goods, but it's about moving the right goods to the right place at the right time. During disaster, a supply chain can break down. Traditional logistic system can always collapse under certain pressure. In such conditions, organizations rely on air freight due to its speed and also the flexibility that we can provide to them. However, air transport comes with a very high cost and also it has a very strict constraints. A single mistake in selecting cargo can delay critical aid or even disrupt entire supply chain. So moving to we are going to discuss about the crisis logistic overview. On the crisis logistic overview, let's imagine there is a manufacturing plant is at risk of shutting down due to a few components are stuck in certain region that affected by a disaster, maybe such as flood. Or even a medical team can also in the need of send an emergency supplies to an isolated area after an earthquake. Time is very limited here, and the available cargo space is only 150 kg. The logistic planner now faces a complex question. What combination items should we ship to have a greatest impact without exceeding the weight limit? This is exactly the type of situation we are modeling in our project. Our simulation includes 20 essential cargo items, each with a weight and also a priority score that reflects its urgency. The challenge is to select the most valuable set of items without violating the aircraft constraints. So, when we touch on the constraints, let's move to see the objective and the constraints that we are facing. Our primary objective is to maximize the total priority score. A numerical representations of each items are important, but we also facing some constraints here. The constraints are a little strict where we must not exceed a total weight of 150 kg. Each item can either be selected or not. There is no partial selection that can be done here, and the decision must be made very quickly, ideally in real time scenarios. This makes the problem ideal for a 0-1 knapsack formulation and also highlights the need for an efficient and practical solution method, especially in high pressure environment. So, to discuss further on the next methodology, I would invite my co-member of the team to continue with the presentation. Over to you, Zulhaimi.
Thank you, Chitra. For project scope, this study focused on selecting cargo items for emergency air freight during global disruption like natural disaster or supply chain breakdowns. We simulate a scenario where a company urgently needs to ship essential components such as semiconductors parts. 20 critical items are considered. Each has a weight and priority score based on its urgency and importance. Since a freight is expensive and has strict weight limit, only items adding up to 150 kg can be selected. Okay. The challenge is to pick the best combination that maximizes the overall priority score without exceeding this limit. This mirror decision logistic team face in real life, where every kilogram counts and every hour matters. Okay, next for methodology. Okay, VBA local search methodology. Step by step. We tackle this using a local search technique implemented in Excel VBA. Here's how the process works step by step. Okay, first step, generate a random feasible solution. The program randomly select a combination of items to be feasible. This combination must respect the weight limit, meaning it must be 150 kg or less. Okay, second, generate 10 neighbors. The program creates 10 new solutions called neighbors by tweaking in initial selection. This may involve swapping one item for another or flipping an inclusion from 1 to 0. Okay, next. Check feasibility of neighbors. Each of the 10 neighbors is then tested. If a neighbor exceeds the weight limit, it's discarded. Only feasible neighbors are kept for the next step. Next, the remaining feasible neighbors are evaluated based on their total priority score. This reflects how urgent or valuable the items are. And finally, from the feasible option, the one with the highest priority score is selected. This becomes our best solution, identified through an efficient local search process. Okay, next. Next, I will pass for result overview to my colleague, Akilah.
Okay, thank you, Zuhaimi. So now I will share my Excel file, how the random and local search button works. So I believe you guys can see the screen, right? Okay, so the random button will generate the selection of 0 and 1 in column D, which means A is the item is selected and 0 means that the item is not selected. This simulates, this code simulates the random attempt. Okay, however, not all random selections are valid. So this loop keeps generating new random solution until the total weight of selected item is within the weight limit, which is 150 kilogram. This is to ensure that the random solution is always feasible. Okay, I will show you a demo on random button solution. So when we click the random button solution, it will give the solution which is in column D with 0, 1 selected item, and then the total weight is still within the limit, which is 96 within the limit 150 kilogram, and then it shows the total score of the selected items. Okay, next. Once we have the feasible random solution, we try to improve it using local search. Okay, this section copies the random solution just now, and then we randomly flip one item, which is changing it from selected to unselected or vice versa. Okay, this will create a new neighbor solution. So this code is what it doing, which is the flipping item. Okay, and then after flipping, we check the new solution. Wait, whether it's still within the limit, and then if it's still within the limit, we keep it as a feasible neighbor, and then we compare it to the others. I mean, we compare the score to others. So this is the code that show that we keep it all the total weight. All the total weight within limit, and then we compare with the others neighbors, and then we don't just stop at one neighbor. And these loops, at here, we do the code as do while neighbor count less than 0. Okay, this loop keeps generating new neighbors, each with one flip item, until we have a 10 feasible one. And then this gives us more variety and better chances of finding the best neighbor solution. Okay, after that, each 10 neighbors that have been generated is written into the sheet from column I to column R, one column per neighbor. Okay, this way we can visually compare all the 10 solutions side by side. Okay, after that, from all 10 neighbors solutions that have been generated, we select the one with the highest total priority scores, and then the best solution is written in column H and highlighted in the green color so it's easy to spot. Okay, so I will show you the demo on how local search button works. Okay, when we click the random solution, right, so it will show you the total weight and total score, which is total weight is still within the limit, 150 kilogram, and then we click the local search. Okay, as you can see, it will pop up a box, and then it show that 10 neighbors generated, and then the best neighbor displayed in column H. So when you click OK, so this is all the 10 neighbors generated, which is from column I to column R, and then the best solution from the column the best solution based on the 10 neighbors is displayed in column H, which is the best solution is that 557 total scores, which is within the limit, which is 140 total weight. Okay, and then finally, we go to the local optimum and global optimum of preference weight. Okay, this local optimal and global optimal of preference weight graph will keep changing based on the 10 neighbors generated here in column I to column R. Since this is a maximization problem, the highest value in the graph is referred as the global optimum, which corresponds to the best solution in column H. So in column H, we have 557, which is the best among the best among the 10 neighbors, and we can see that this is the global optimum, 557. Okay, that's it from me. I will pass to Zuhaimi back for the conclusion. Thank you, Zuhaimi. The floor is yours.
Okay, thank you, Akilah. I will continue with discussion first. This local search method help logistic planners choose cargo more efficiently during emergencies. By picking the right item based on priority and staying within the weight limit, it improves planning and reduces costs. The algorithm tests different combinations and find better ones by flipping selection. This makes decision making faster and more accurate when time is critical. It is a smart way to solve the 101 knapsack problem and support logistic team in crisis situation. Okay, next slide. For conclusion, our group assignment successfully applied a local search method via an Excel VBA application to address the 01 knapsack problem in emergency logistic context. The VBA program was designed to create an initial random solution and then improve upon it by exploring feasible neighbors. The best neighbor with the highest priority score is identified as the optimal solution within the scope of the local search. This approach demonstrates how local search can be a practical tool for finding effective solutions in high-pressure logistic environment with limited resources. Okay. Thank you again for your attention and support. We look forward to any comment or suggestion you may have.